Hi guys, this is Mrs. Allison. Today we are going to be talking about one of the next applications of derivatives that is used a fair amount, which is optimization. So we've looked at one already, which was related rates. And today we're going to look at another one that seems similar and is pretty similar, just different process, called optimization. But before we begin, I would like to do a brief warm-up. Hopefully it looks a little familiar to you based off of the test that you guys have back. Some of you have back, sorry. And so I'd like you to hit pause and try these 3 examples. Okay, these 3 examples all come from the definition of a derivative. So let's review the idea of a definition of the derivative. Okay, first, if we want to deal with the definition of derivative. If we want to deal with the derivative as a function, we would write it as f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x all over h. Would be the derivative as a function. You can also see it written as delta x instead of h. Either one is fine. They mean the same thing. And remember that we have the derivative at a point. And that would be that f prime of a, some point a, is equal to the limit as x approaches a. Sorry if you can hear my dog in the background. Not sure why she came in the room. As x approaches a of f of x minus f of a all over x minus a. You guys, this is what we're dealing with here. This is the derivative at a point. And remember how I said you will see one of these questions on the AP test. So these 3 examples are prime examples of what you could see. Okay, what you could see here. Now, for this first one, if we look at this first one, it says the limit as h approaches 0 of sine of x plus h minus sine of x over h. Hopefully what you recognize here is what they're giving you is that the function here is sine of x, and we are asked to take the derivative. So if I take the derivative here, f prime of x, I don't even need to use the limit definition, would be the cosine of x. Because if we were to use the fact that h approaches 0, we would get 0 over 0, which would be the indeterminate form. And that's going to happen. And so I need to recognize what this could be. I don't really have a great way I could simplify this without using the limit definition of a derivative. Okay, so let's look at the next one. What is the next one saying to us? If we say the limit as x approaches 2 of e to the x minus e squared over x minus 2, you have to keep in mind what this is really saying is, hey, my function is e to the x, okay? But what I want to know here is the derivative of that function at 2, okay? So the first thing I'm going to do is I'm going to take the derivative of f of x, so we get f prime of x equals e to the x, and if I evaluate that at 2, we get e squared. So my answer to this problem is e squared. Okay, so let's look at this third one. If we were to take the limit as it's written right here, the problem is I would get that indeterminate form. Now this one I could actually simplify, but what a mess that's going to be. So what is the function that's listed in here? Even though it's not written exactly how we would write it, what is the function? Well, the function that's written in here is f of x equals the square root of x minus 2. And what they're asking us to find is what is the derivative evaluated at 4. That's what we're looking for. So I'm going to take my first derivative here, And if we take the derivative of this, if you remember your square root rules, it would look like this. We'd have the chain times 1, so that works out okay. And if I now evaluate this derivative at 4, we get 1 over 2 square root of 4 minus 2, so we get 1 over 2 root 2. Okay, so how did you do on those? Hopefully you start to recognize that any one of these could come up, limit definition of a derivative, could come up on the AP test for at least one multiple choice problem. Okay, well, let's move on to what we actually want to talk about today, which is the optimization story problems. Okay, so as I said before, there are two pretty common applications for derivatives. And one of them is related rates. The other, that actually is probably even more useful in more fields, would be determining max and min values, or what we call optimization. Okay, and just like before, there's a set of steps we're going to go through that tend to make this a little bit easier. The first one being, we're going to choose variables, and I like to draw and label a diagram of some sort of figure. We're going to write a primary equation, meaning what is it we're trying to maximize or minimize. So this primary equation comes from whatever is to be maximized or minimized. So when we look in the story and we see we want to maximize area, for example, we're going to write an equation relating area. If it says we want to minimize costs, our primary equation is going to be costs. Okay. Then what we're going to do is we're going to rewrite with only one variable on each side. So this sometimes requires a secondary equation, because sometimes we don't have a single variable on each side and we need to get there. Then we are going to find the domain. Why? Well, the domain here is our endpoints, or we can use it to consider our endpoints, because we may need to look to see where the function can actually occur. So it could be possible that what we find as our max is not actually in the domain of the function, or we may need to consider our endpoints for part of that domain or part of the max or min, and we'll look at that in just a minute. Then what we're going to do is we're going to take the derivative, find the critical numbers, and make a number line, etc., and go through the rest, same steps we've been doing to find our maximum or minimum of just general functions. Pretty straightforward. So let's look at an example. Okay, so let's look at this first example. It says the sum of two non-negative numbers is 30. Find both the numbers if the sum of twice the first plus the square of the second is a maximum. So as I said before, the first thing we want to do is write an equation based on what we're maximizing or minimizing. So in this case, we're doing both, maximizing and minimizing. This statement that says, find both numbers if the sum of twice the first plus the square of the second is a maximum. So let's start with defining our variables. So let's let x equal the first and y equal the second, just so we know what we're talking about. And what it says here is find both numbers if the sum of twice the first, that's an x, twice the first plus the square of the second is a maximum. So this is what I'm trying to maximize. Okay, the problem is, as we said before, we wanted to make sure that there was only one variable on each side. And right now I have three variables. I have the maximum I'm trying to find, I have x, and I have y. But I do happen to have a secondary equation. And that secondary equation is this first one that says the sum of two non-negative numbers is 30. This also happens to have my domain. Okay, so keep that in mind. We're going to plug that in. We're going to write our secondary equation that's going to be x plus y equals 30. Two non-negative numbers that sum to 30. What that means too is we need to consider our domain for this needs to be greater than or equal to 0 for both of them. So x is greater than or equal to 0, y is greater than or equal to 0. Okay, so let's solve this for either x or y, and my suggestion might be to solve for x. Doesn't really matter, but let's solve for x. So we get x equals 30 minus y. Now I'm going to go back into the original equation, and in place of x, I'm going to write 30 minus y. So then I get 60 minus 2y plus y squared equals the maximum that I'm trying to find. And we know that in order to find either the maximum or the minimum, it doesn't really matter what I'm trying to find. But if I'm trying to find the maximum or the minimum, I'm going to need to take the derivative of this. And in taking the derivative of this, I'm going to get that we have negative 2 plus 2y equals, I'm hoping for a maximum. So we're just going to put 0 because I need to find my critical numbers. And we get 2y equals 2, which means y equals 1. Okay, so if y equals 1 and we were to start a number line chart with this, a first derivative chart, and we plug in 1, really this should have said, sorry, f of y, because we took the derivative with respect to y in this case. So let's just go change that. And if we plug 1 into my first, or a number less than 1, but greater than 0 in, something like a half, if we plug in a half into negative 2 plus 2y, we will see that we get a negative number. And if we plug in something like 2, 3, 5, anything else, I get a positive number. So here's the problem. I'm right now trying to find a maximum. And what do I see about 1? It's a minimum. So what else can I consider? What else have I not thought about? Well, I've got my domain that I need to consider. Now, I originally said the sum of two non-negative numbers is greater than, two non-negative numbers, which meant x was greater than or equal to 0, y is greater than or equal to 0. But do I have a max at that point? Is there any place that it can't go above? Right, so let's reconsider this domain. I'm just going to rewrite it. Let's rewrite this domain and let's say instead of just greater than or equal to 0, let's rewrite it and say, okay, I know it needs to be greater than or equal to 0 for both x and y, but at the same time, it also has to be less than or equal to 30 because I can't sum to 30 if one is greater than 30 unless I use a negative number, and I can't do that. So we need to consider my endpoints of 0 and 30. So we're going to treat this like a problem where we were dealing with the absolute max or min. And I'm actually going to just look at my values here. So let's plug in 0, 1, and 30. Maybe that'll help me to see what's going on. If I plug in 0 for y, let's go back to the equation where, we'll go back to this one. If I plug in y for 0, we get 60. If I plug in 1 for y, we get 60 minus 2, 58, plus 1 is 59. And if I plug in 30, 30 would be 60 minus 60 plus y squared, which would be 30 squared, which would be 900. So where is my maximum? Right, my maximum is when y is 30. So my maximum occurs when y is 30, and x would then have to be 0. Y would be 30 and x would be 0 because that's the only way that they can sum to 30. Okay, so what about the minimum? Well, my minimum would need to be, my minimum value would be 59, but my minimum would happen when x equals, when x equals 29 and y equals 1. Now, could this work the other way? What if we switched the variables around? Just watch for a moment. What if instead we had 2x plus y squared equals, we're trying to find the max, and instead I solve for, in the secondary equation, solve for y, and we get y equals 30 minus x. Then over here we'd get 2x plus 30 minus x squared equals my max. Now I could FOIL this, I could take the derivative as it stands, it's up to you. If we take the derivative, we'd get 2 plus 2 times 30 minus x times negative 1 equals 0, and I'm trying to solve that. So we get 2 plus, that'd be negative, oh my goodness, negative 60 plus 2x equals 0. So my problem would say 2x minus 58 equals 0, and I'd solve. So we'd get x equals 29. And if I tested 29 in a first derivative chart, this time with f of x, okay, we would get 29. If I plug in something less than 29, like say 1, into my first derivative, we'd get 2x minus 58. It'd be negative, so it'd be decreasing to 29. And then if I plug in 29.5 or 30, we would get a positive number, so it'd be increasing. So we know that 29 is my min. X equals 29 is my min, which is what we said. So it really doesn't matter if we switch the order. It just matters if we understand what we're solving for, the max or the min. Okay, let's move on to another problem. Okay, so this says a box with no lid is to be made from 48 centimeters squared of material. If the box must have a square base, find the dimensions that produce the maximum volume. Explain the meaning of the answer with a complete sentence. Oh, we'll get back to that. Okay, let's start with what we're trying to maximize. We're trying to maximize volume. And we know volume is length times width times height. Okay, so let's look at it in terms of our problem. A box with no lid is to be made from 48 centimeters squared of material. The box is to have a square base. That square base, that's important. So let's go and label our bases. Let's just call them both x. Okay, which means we don't know the height. So let's go ahead and call it whatever you want to call it. Z, x, we can't call it x, sorry, z, h. We'll just call it h for height. Okay, so I could rewrite this volume equation to say that the length and the width are x times the height, which is h. So this would be x squared times height. Okay, well here's the problem. I have too many variables. So what secondary equation could I write? Hopefully what you noticed is that they gave us a surface area. Okay, they told us that the amount of material that we need is 48 centimeters squared. So this is the surface area. Well, let's think about the surface area of a box with no lid. Okay, so I have 4 rectangles around all the sides. So 1, 2, 3, 4. 4 rectangles around the side that are all XH. So there's 4 of those. Do you agree with that? And then I have the final piece is I have an x squared. Okay, so this is equal to 48, or the surface area. So let's use this information and make a substitution. So is there a variable that looks easier to substitute for? Well, I would argue getting h alone is going to be the easiest. So let's do that. Let's get h equals, that would be 48 minus x squared over 4x would be my height. So now let's substitute this into the volume equation. Volume equals x squared times this beautifulness, 48 minus x squared over 4x. And then let's simplify that just a little bit. If we simplify this, we would get x over 4 times 48 minus x squared. Still don't love it. Let's do 48 divided by 4. 48 divided by 4 is 12. So we'd get 12x minus a quarter x cubed if I distribute that through. So really what I'm trying to find the maximum of, maximum volume, is the volume which is 12x minus a quarter of x cubed. So if I take the derivative of this, the derivative of the volume with respect to x, I would get 12 minus 3/4 x squared. Solving this for 0, we get 0 equals 12 minus 3/4 x squared. 3/4 x squared equals 12. I did it in a little bit of weird order. If I multiply that across, we get x squared equals 48 divided by 3, which is 16. And so x equals plus or minus 4. Okay. Well, let's think about our domain here, which is something we haven't considered yet. If we go back and think about our domain, and I'm going to write it above the box, what is the smallest amount of material I could use on any side? Although it doesn't make a whole lot of sense, but still the smallest amount of material I could use. Well, the smallest amount of material I could use for x is going to be 0. I don't know how that works to have a dimension of a box that's 0, but it is the smallest. Maybe we want to say x is greater than 0. But what's the largest? How would I figure out the largest amount? Well, the largest amount that x could be would happen if h were 0. So looking at this equation that we solved right here, if h were 0, then the largest amount of material that x could be would be when 48 minus x squared equals 0, which means x squared equals 48. So when x is positive root 48. We can't have a negative distance. That wouldn't make sense. So my largest value for x would be positive root 48. My lowest value for x would be 0. Okay, so I have my endpoints. So let's look first of all to see if the value of positive 4 happens to give us a maximum or a minimum, depending on what we want. We just want to check. We're just verifying. This isn't actually going to help us answer the problem. But if I do my first derivative chart and I consider positive 4, if I plug in a number, say like 2, into my first derivative, so if I plug 2 into here, 12 minus 3/4 of 4, so 12 minus 3 is a positive number. And since it's a positive number, I know my original function is increasing. If I plug in something like 5, square root of 48 is just above or just below 7, so we're fine if we plug in 5. If I plug in 5 into this equation, 5 squared is 25, 3/4 of 25 is actually less than 12, or bigger than 12, so when I subtract them, it will be a negative number. And so then we know 4 happens to be a maximum. Since 4 is a relative maximum in that area, we don't really need to consider either 0 or root 48. You could certainly look at them. We could always make a table of values here and consider 0, 4, and root 48. And if we plug those into our original volume function right up here and get a value, 0 is going to be 0. I like that. 4 is going to be 12 times 4 minus 1/4 of 4 cubed, which is 32. And if we plug in the square root of 48, doing the same thing, let's see if we can get that. Sorry, I should have done these numbers ahead of time. Square root of 48 cubed. Yikes. We get a negative number, and it's pretty large, so we're going to ignore that one. We know that the maximum has to be at 32. So if we were to give a complete sentence, since it said this, we would say the max volume, it's nice to include what it is, of 32, we would have centimeters cubed, occurs when x is 4. And then you could even substitute in to find the height if you wanted. So if we substitute in 4 and do 48 minus 16 divided by, that would be 16, would be 2, when x equals 4 and h equals 2. Okay, that would be a box with no lid that would have a max volume. Okay, let's look at one other type of problem. Okay, these are common where they're not actually a diagram of a shape, but they are on a coordinate system. So a rectangle is positioned with one vertex on the line y equals -1/2 x plus 3 in the first quadrant as shown. Find the point so that the rectangle has a maximum area. Okay, so we know what we're trying to maximize. We're trying to maximize area. So I'm going to write an equation based on area. Pretty straightforward. If we're on a coordinate system, the area is going to be x times y. X because the length of x, y times the length of y. We've got that. Now, the nice thing about this one is I don't even have to write a secondary equation. It is written for me. Not only is it written for me, it's already solved. So my secondary equation is the equation y equals -1/2 x plus 3. And so I'm going to go ahead in my area equation and I'm going to substitute that in. So we get -1/2 x plus 3. And now let's find, let's simplify it maybe a little bit more. Area equals -1/2 x squared plus 3x. And now let's take the derivative of area with respect to x. And we get -x plus 3. So 0 equals -x plus 3. So x equals 3 is my critical value. It's where I'm going to consider my maximum to be. But now we need to think about our domain. Let's think about our domain for this particular function. Well, we know that x needs to be greater than or equal to 0 because it said it's in the first quadrant, okay? But the x value right here, how would I figure out what that is? Well, if we know this is the line -1/2 x plus 3, and I'm trying to figure out where y equals 0, I would say 0 equals -1/2 x plus 3. So we get x has to be 6. So this crosses the x-axis at 6, which means the largest x value I could have is 6. And since we're trying to figure out a max area, we could certainly plug in all three of these values, 0, 3, and 6, into my function, my area function. Let's change that to say area function. I don't know why my eraser is such a tiny dot right now. Let's change that to say the area function, just so we know. We could plug it in there to figure out which one's the max. 0 is going to be 0. 3 is going to be -1/2 of 9 plus 9, so 4.5. And 6, if we plug 6 in, is going to be -1/2 of 36, so -18 plus 18 is going to be 0. We know where our max is, but we could also have done this using our first derivative chart. And we could have seen that our max would have occurred at 3 if I considered what happened before, like say plug in 1. If I plug in 1 to my derivative, I get a positive number, so that means my original function's increasing. If I plug in 4, I get a negative number, which means my original function is decreasing, which means this has to be the maximum. Okay? So if we give a statement about this one, we would say the max area. You could even give the max area if you wanted. The max area occurs, I can spell, occurs when x equals 3. Maybe we want to say what y is, and y is, plugging that in, we would get 3/2. You may even want to say the max area is, and plug it into the area formula. And if we plug that in, we'd get 3 times 3/2, which is 4.5. So that's an optimization problem. Hopefully that makes sense. Today, what you're going to be working on and into tomorrow, so you have, just like with the related rates, is an optimization circuit to practice some of these problems. So let me know if you have any questions, and we will see you soon.